So consider a triangle family, these blue triangles, interscribed, as before in previous video, interscribed between an outer ellipse and an inner circular caustic. Okay, now I've implemented here in GeoGebra the formula that calculates the radius for a circular caustic given the position of its center that it can flexibly drag using GeoGebra. Okay, and then for any position of that center C, I have the Cayley n equals 3 condition is satisfied, meaning that I do close on n equals 3 family. Okay, now what I want to show in this video are the loci of triangle centers of these blue triangles over the specific family, and I want to study how they vary as I drag C around the plane. So for example, by definition, the caustic is the incircle of this family of triangles, and over the family, the incircle is stationary. So I'm just showing x1, the incircle, stationary over C. How about, so just to give an illustration, what I'm trying to do is I'm actually investigating the loci as I vary C, right? So x1 is always going to be stuck over C as I vary the family. How about x2, the barycenter? The barycenter, we've shown elsewhere, okay, and it's been shown elsewhere that the barycenter is always an ellipse. Its axis aligned with the outer one. It's actually homothetic with the outer one, right? So it doesn't matter where C is, I'm always going to get this homothetic ellipse. A phenomenon that looks interesting here is that there's positions for C where the ellipse, the locus of x2 reduces to a point. So I can see that there could be a whole family. Oh, doesn't look, yeah, there could be a locus of x2s, and I have to study there, for which, sorry, there could be a locus of c's for which they collapse. Okay, so there are 2 points where they collapse, and they're probably easy to calculate. Very well. Let's look at x3. Now, x3 is elliptical. We've shown this in a previous video. So in fact, over any Poncelet family, the locus of any triangle center, which is a fixed linear combination between the barycenter and the circumcenter, x2 and x3, is going to describe an elliptic locus over the family, right? So you can see here that x3 is describing an elliptic locus. And we see here that additionally, the major axis of x3 seems to contain C, right? So wherever C is, you can see here that that major axis is pointed towards C. Now, I would say that this, we've already shown this elsewhere. Okay, so this is pretty cool. Now let's look at, so an idea for an experiment here is what happens to this locus as C traverses one of those isoradius curves that we suggested are ellipses in the previous videos. Do we think that this locus is going to have an invariant if the radius is invariant? For example, is it going to conserve radius? Is it going to conserve aspect ratio? So these need to be investigated. How about x4? x4 has an interesting property. It's always an upright ellipse, and I believe it is homothetic. It's homothetic to a rotated version of the outer ellipse. Okay, so I believe we have shown this elsewhere, and you can see here that there's also a condition in which x4 shrinks to a point, the locus of x4, and that point shrinks exactly on the focus of the outer ellipse. That's kind of cool, right? So we need to investigate that dynamically as well. I don't think we have actually documented this particular property anywhere. So there's a position for C on the major axis that shrinks the locus of x4 to a point, and this does not occur. In the minor axis of the ellipse. Okay, I could change the aspect ratio of the ellipse, make it be more like that to see if that phenomenon continues to occur. Yeah, it looks like x4 always shrink to a point locus for 2 positions of C, and that point locus is going to coincide with the focus of whichever outer ellipse I'm talking about. Okay, let's look at some other points because I've noticed some really cool phenomena here. Let's go to x5. So x5, we know it's always an ellipse because it's a fixed linear combination of x2 and x3. Now, there's a phenomenon here that seems to be manifesting. The center of the circle seems to be on one of the foci, and this, I'm just eyeballing this, right? If x5 is an ellipse, it looks like these ellipses have one of their foci right on C, okay? This looks to be true here, just eyeballing it needs to be proved. But this is an interesting phenomenon. Okay, now let's go to x6. x6 is not a linear combination of those two triangle centers. And you can see here as you approach that this curve does not look like it's an ellipse, at least to the naked eye, but it could be, right? I think it's less likely that x6 is an ellipse, and I don't care much about x6 for this particular discussion. I want to show you a couple of other phenomena that are quite interesting. Let's look at x7. x7 seems to be an upright circle or ellipse, okay? I would hazard that this is an ellipse. You can see here, but maybe this is not elliptic. We would have to check that. And it's also shrinking to a point somewhere. I don't know. We'd have to study that. Yeah, it's not a point there. Let's try to exaggerate that to see if there's any. You can see here that it's deviating from a point over here. Yeah, but when C is on the focus, perhaps this is kind of a different phenomenon. When C is on the focus, so in this region here, x7 seems to be shrinking to a point. So we need to study those singularities as well. Okay, yeah, let's do that. Yeah, that doesn't seem, you see if I zoom that, it's not a point as x3 was a point, right? As we saw that phenomenon for x3. Was it x3 or x4? Let's see here. Oh, maybe it was x4. x4 shrunk to a point. Yeah, it was x4 that shrunk to a point for a particular position of C. But if I go to x7, you can see here that it does not shrink to a point over F, but I believe when perhaps some other intermediate location here, it is shrinking to a point, okay? So interesting. Now, a nice superstar is x8. Let's look at what happens to x8, okay? Now, x8 surprised me. It's always an ellipse, and its axes aligned and concentric with the outer one. Perhaps it's even homothetic to the outer one. So we need to prove that x8 is always an ellipse, okay? And that it's perhaps homothetic to the outer one. We have to check that, okay? But I thought this was pretty cool as well, and you cannot zero it out. It's always, it has some finite area. Now let's explore some other triangle centers here. How about x9? x9 seems to be an ellipse, the Mittelpunkt, and it's always axis aligned. It's not always axis aligned. It's actually tilting a little bit. So it could fool our eye, and this could not even be an ellipse. We have to show that it is, right? But let's keep moving. Here's x10. x10 seems to be axis aligned. Okay. Now, I want to know, well, x11, the Feuerbach point is necessarily on the circumcircle. So its locus over Poncelet is going to be, sorry, I said circumcircle, I meant incircle. Its locus is going to be the incircle, okay? So there are no surprises here. Let's keep moving. I want to show you guys a few interesting results. So, for example, yeah, let me fast forward. Yeah, you know that x20 is a reflection of x4, so it's going to be something interesting too, right? I think it's a reflection of x4, perhaps x3, something like that. So it's going to be an ellipse, and it's going to have some nice properties. But I actually want to fast forward here over these other triangle centers, and I want to go up to triangle center that I'm fascinated with, which is 59. So 59 is always a treasure, right? So you can see here that you have a palette of very interesting loci for x59. Okay, it looks like it's a regular curve. I don't think this thing is a proper cusp over here. Let's change the aspect ratio of the outer ellipse. You can see here that the curve that x9 sweeps, it's fascinating, right? So it has this whole richness here. We've seen things that are similar like that before. So yes, I love x59, and we should explore this. Although this is kind of like in the artistic domain already, right? So here's x59 for you. Okay, you can see it can be as simple as something like that. No self-intersections when C is close to the boundary, but as you start approaching the center, it wants to curve on itself and then, you know, change its topology. Quite interesting, right? So here's the new topology with several self-intersections, 4 self-intersections, and then here you have no self-intersections. Quite cool. Okay, now let's look at some other examples here. I saw some other cool examples. Yeah, so here's x65. This looks pretty circular to me. That would be interesting, right? To prove that this thing is circular. Let me advance here. Was another thing of note, I believe. Yes, 80. 80 was quite cool, and I think I'm going to finish on 80. 80 looks like a circle everywhere, and it's a circle that is concentric with C. Okay? Is it twice the radius of C? It looks like it's even twice the radius of C, perhaps. Okay? Let's see if there's a way for us to check that. Yeah, you know, eyeballing it, it looks like x80 is always a circle, and it's a concentric circle with double the radius. Any other ones? Let's see here. I don't believe I saw anything else that interesting as I move forward. 88 is always interesting. It's like a cousin of 59. And it tends to have some interesting geometry as well. You see it goes through a self-intersection up there. Cool, cool, cool. Anything else? 89. Oh, look at this one. This is 90. Yeah, so 90 has like some phase changes here, but it's not elliptic. It's not a conic. Yeah, so here's 93. 93 is cool too. Look at that geometry of 93. Okay, almost looks like one of those lemniscates, right? Or analemmas, if you like, astronomy. How about 94? 94 looks like has a panhandle kind of thing. Let's look at it. Yeah, it has a panhandle, right? 94. Look at that. Yeah, very complicated geometry. How about 95, 96, 97, 98, 99, and 100? Let's stop here. And I want you guys to review this video to see some of the phenomena that we went over from k equals 1 to k equals 100. These are loci of Poncelet, and I would say here a very cool guy is k equals 8. What is this called? A Nagel point. That you get the sort of a stationarity and an ellipse regardless of where you are. So there's like definitely a harmony here with x8. Then we got this really cool thing. Looks like the multiples are working here, right? And x80, where you get this sort of concentric circle, right, over Poncelet, twice the radius of C. All right, maybe this is obvious. Maybe x80 is always located on a copy of the incircle that is twice the radius of the incircle. So this is not interesting at all. All right, see you guys in the next video.